Welcome, everyone. We're very happy today to have Jelena Diakonikolas. Jelena has an interesting background. She worked during her PhD in networked systems at Columbia. And then she saw the light and started to work on convex optimization. And she will tell us about that.
Yes, thank you for the very interesting introduction. The talk, as the title suggests, will be about a very general technique for the analysis of first-order methods. And then we'll see how we can use this technique to both recover known methods and get some new methods and get some results in even non-traditional settings of convex optimization. The setting for this talk is the standard setting of first-order convex optimization. We want to minimize a convex function. Let's assume it's also differentiable. In some cases, this is not essential, but let's keep things simple. We want to minimize it over some closed convex set. The information we are allowed to use is the information about the function's gradients. So this is known as the first-order oracle model. What it means is that there is a black box. We feed it a point from the feasible set. And what we get is the gradient at that point. Some models also assume that we can get function value at that point. For this talk, that won't be necessary. Now, this setting is not new. In fact, there has been a lot of research on different settings of first-order convex optimization. And we know about methods with optimal iteration complexity in various settings. Now, why am I talking about this? There has been lots of interest into first-order methods because they are typically not very computationally expensive when it comes to the dependence on the input size. So they typically need few iterations, and per iteration, their cost is typically near linear in the input size. So these methods are very frequently used in machine learning on problems like regression, classification, training of support vector machines, etc. What has been the case for a long time is that the analysis of these methods often seems unintuitive, and it is not always clear how to generalize it when we work in some less traditional settings. And we will see later what this less traditional means. So the big picture of this talk is that I will first tell you about a general technique. This general technique relies on a notion of an approximate duality gap. This approximate duality gap will be the difference of some upper bound on the optimum of the solution and the lower bound. The upper bound will have some notion, will be related to the primal problem, and the lower bound will be related to a dual problem, and we'll make this more concrete. Now, from this general technique to actually get methods, we can show that if we work in continuous time by enforcing an invariance principle, which is like a conservation law, we can get different first-order methods directly out of that invariance principle. So this will be fully constructive. If you think about work on continuous time methods, there are two main views you can take. If you remember things from your physics classes, in physics there are these two main views. One is a Newtonian view, if you wish, where you have some action in the system, and then you try to describe what is happening to it, right? So in optimization, this means you have an algorithm, you sort of guess what the algorithm is, and then you try to analyze it. And this was the view that was taken even in the original work by Nemirovsky and Yudin. They used this continuous time interpretation as a motivation for mirror descent. And it was more lately used to explain the phenomenon of acceleration. Now, there is this different view, which is Lagrangian view, where you have some conservation laws, you have some invariance in your system, and based on those conservation laws, you get what the path of your system is and how your system should behave. For us, what this will mean is that we will see some conservation law, and from there, we will get an algorithm. Now, there is more recent work that is closer to this view. However, it is not fully constructive. You still need to have a guess of what the conservation law should be, and it's not really conserving. The work I'll talk to you about today is fully constructive, and everything you'll see will come directly from optimization. Now, based on these continuous time methods, we will look at some classical methods of discretization, and I will give you a few examples on how to recover known methods and also obtain new methods and results. In the discrete time, I will mainly be illustrating things on the example of accelerated algorithms. Then, for less traditional settings, we will see how we can use this technique to also obtain results in the model where we don't have exact gradients, but they are corrupted by noise, and I'll tell you also when this happens. And the technique can also be generalized to other non-traditional settings, such as the setting of width-independent algorithms and the setting of block coordinate descent. It's quite ambitious. I'm not sure if we'll get to everything, but hopefully we will. So let's start with the first part. At a very, very, very high level, so you zoom out 3 miles, the general idea is as follows. We are minimizing this convex function, so we want to find this minimal solution. This is our minimum function value. Everything that lies above it is an upper bound to it. Everything that lies below is a lower bound. So the difference of the two is some optimality gap. Simple enough. Let's make it a little bit more concrete. To do so, I will need some notation. So we will use ut to denote an upper bound at time t. And this ut will have some associated primal solution to the problem. There will be an lt, which is a lower bound at time t, and it will have an associated dual solution, zt. The gap is just the difference of the two. And also important for this construction will be this strictly increasing function of time, alpha t. This function is essentially what will determine our convergence rate. So if alpha of t is t squared, we will get convergence of the type 1 over t squared. To make things simple, assume that it is 1 at the initial point. It can be any constant. Doesn't matter. So the main idea, super simple. What I want to conserve over time is alpha of t times gt. So my gap scaled by a strictly increasing function of time. If this is the case, then it immediately means that my gap decays as 1 over alpha t. It is the initial gap times this, which is just 1 over alpha t. Right? There are some basic requirements. That is, as I already mentioned, I need to be able to map my upper bound to some actual solution. My lower bound should really be a lower bound, which will be by construction. And the initial gap should be some notion of initial distance to the optimum. So if we have this, then it immediately implies the convergence of the type that we are used to seeing in first-order methods, which means that the distance in the function value to the optimum is the initial distance over alpha t times some constant. OK, so let's see now what this upper bound and lower bounds are. Upper bound, very easy. This is a minimization problem. So if I take any point from the feasible set, if I evaluate the function on it, that's an upper bound. It must be greater than or equal to the minimum value, right? In particular, if I'm running any algorithm, I can take my upper bound to be the function value at the last point I constructed, or it can be some convex combination of the function values at all the points I have seen so far. And this type of choice makes sense, and I can map it to an actual solution due to Jensen's inequality, which tells me that the function value at the convex combination of the points is less than or equal to the convex combination of the function values at those points. So this works. Now, what is more interesting is the actual lower bound. Because my function is convex, and for now I'm assuming also it's differentiable, if I have any point from the feasible set, and I have a gradient, that defines a lower bounding hyperplane. This can even be used as a definition of convexity. All it says, linear approximation of a convex function lies below a convex function. Or if I put a tangential plane, my convex function is above it. Right. So what I can do, I get more points, I get more lower bounding hyperplanes over time, and so I can take any convex combination of those lower bounding hyperplanes. In particular, here I will use this function alpha I mentioned before as my measure. So this a of t is just the integral of d alpha of tau. I'm introducing a of t because the same thing will be true both when alpha is a discrete measure and when it is a continuous measure. So the same construction can be used both in continuous time and discrete time. Okay? Now, this convex combination of the lower bounding hyperplanes is just another lower bounding hyperplane. But if you're careful enough, you can already see an issue with using this directly. The issue is that this lower bound depends on x star, which is my minimizer. And this is not something I know. It's something I'm trying to determine. So I cannot really evaluate it. One thing I could do is just take the min on the right-hand side and remove this x star. If I do that, that's also not a particularly good idea because what is happening is that every time I query a new point and the gradient, when I add them into this convex combination, my lower bound may change by a lot. And I generally want this change to be more controlled. Yes?
Wait, so if you have unconstrained minimization, then you can choose new such that this is like infinity or something?
Yes. In the unconstrained minimization, exactly. It is not useful because in most cases you would just have a trivial lower bound. Right? So let's see how to make it useful. Okay. The idea I believe many of you have seen is known as regularization. So let's say I have some strictly concave function phi. And what I'll do, I'll subtract 1 over at phi of x star from both sides. And if I now take the minimum, this function I'll get here, because this is a strictly concave function, this whole thing will be differentiable. If it is strongly concave, this will even be smooth. So it is much more controlled. And in fact, this will be my lower bound up to this correction for what I added, this regularization error. Not 100% precise, I'm lying a little bit. This is exactly what we use in the discrete time. In continuous time, you just need to ensure that this is well defined initially. I skipped those details because it's literally one more line. You just mix in another f of x star. OK. But let me give you a different perspective on this. Because I showed you how to get here, but not where it really comes from. So a different way to think about this is to think about it as homotopy. So what you're really doing, so let me just call this 1 over at phi of x, call it phi t. So what you're really doing is you're not constructing a lower bound on f. You're replacing f by some composite function, this f minus phi t, and constructing a lower bound on it. So what happens over time if this phi of x star is bounded is that initially this a of t is very small, right? So you may change your function by a lot. But as the time progresses, this a of t is strictly increasing. So your error decreases and you get closer to your original function. If you're familiar with convex conjugates and Fenchel duality, from this lower bound, it would take you 1 or 2 more lines to show that this lower bound, in fact, is exactly is greater than or equal to the Fenchel dual of that composite function. So really what our lower bound is, it is a Fenchel dual of this new composite function that I introduced here. And it is evaluated at the average gradient, which has this notion of a dual solution. So what we're really doing when we're constructing this lower bound is that we replace our original function, this pink function, by this blue-green function. And we track the dual of this composite function. So over time, this dual becomes closer to the dual of our original function. This is the most technical part of the talk. And this is the basic set of arguments from which you can get a very large set of first-order methods. Like some small things may change. If you know more about your function, you may be able to use a better initial lower bound. But the set of arguments, it is completely the same. So let's see from here how to actually get continuous time methods. Actually, before I do so, are there any questions so far?
Can you say one more sentence on how we should see that you get the Fenchel dual? I mean, my issue is that the Fenchel dual of f plus phi or f minus phi is not, the Fenchel dual of f plus the Fenchel dual of phi.
That's why there is greater than or equal to here.
I see.
This minimization, so this is phi t.
Okay, now I get it.
This will exactly give you phi minus phi t star.
It's because it's not equal.
Yeah, yeah. And then for the other part, you just use first order optimality.
Okay.
Yes.
Minimization on negative of phi is phi convex.
Phi is concave, so minus phi is convex.
Okay.
Why?
Huh?
You could just like okay.
I could have added a convex function. Because people tend to write like Fenchel dual for the difference as opposed to the sum, and it just looks nicer because if it was plus, then there would be minus et, and just neater.
Why not so I think the Fenchel dual part is exactly equal to not.
Oh, you think it's exactly equal?
The inequality is due to the convexity of f, right? Or you have f star.
Yes, it's f star.
Okay, right. Then it's
Yes. Okay, good. So let's get to the continuous time methods. I will show you 2, and there are many more, but let's see 2 of them. Okay, the first one is known as continuous time dual averaging or mirror descent or lazy mirror descent. Let's just give a name to the argument of the minimum from the lower bound. So our lower bound, because it has this minimization problem, it generates points from the feasible set. So now, let me take the upper bound to be the convex combination of the function values, exactly defined by this measure alpha. So what happens if you take the time derivative of alpha t gt, and remember, my invariance isn't this, that I'm conserving this. So what I want is that the time derivative is 0. Yes?
So I guess, what should I think of alpha t being? So you said it's like strictly, like, is it
in continuous time, it doesn't matter. If you show it for a linear function, you can show it for any increasing function just by rescaling time.
Okay, so let's say it's 1 plus t, something like this.
Yeah.
Okay.
It is more important in the discrete time because there you cannot get arbitrary stuff.
Why do
Yeah,
you
good.
normalize by 1 over alpha t in ut and not 1 over the integral of d alpha?
Because I'm mixing in the initial solution.
Yes.
This is due to the step that I skipped where I needed to mix in I needed to put in a little bit of mass in the lower bound on something fixed just to have it well defined at the initial time point. Yes.
Can I choose alpha 0, t0 to be 0?
Alpha t0, you can take that it's 1. As long as it's non-zero and it is a constant, it's fine.
Oh, it's scaling about.
Yeah. Yeah, exactly. You can always rescale the function, and I already told you this works for any increasing alpha t.
Can I just want to understand
Yes.
The upper bound should be a convex combination of the function values that I have seen. Shouldn't it?
The convex combination of the function values
that I have visited.
at the points you have seen so far. You had to start from something, right?
Yeah, sure. But why don't this doesn't integrate to 1, the weights? Or maybe I'm
it does, because the weight of this is alpha of t minus alpha t0. So alpha t0 plus alpha t minus alpha t.
I see. Okay. Yeah, thanks.
Yeah, no problem. Straightforward way to make this 0. You have inner product of the gradient and something. Make something 0. And that's your continuous time dynamics. The actual solution that you would output, because you're taking a convex combination of the function values, will be that same convex combination of the points. So a continuous time dynamic similar to this one was an original motivation for mirror descent, but they started from an algorithm and then analyzed it using Lyapunov stability criteria. Here you didn't even need to know what the algorithm was. You get it from the invariance. Now let's see another example. So now if I take my other upper bound and I do the same thing, just make this something else equal to 0, this exactly gives you what is known as accelerated mirror descent dynamics. And you can see that something like this makes sense. If you integrate both sides, you will get that this is in fact the average of the initial point and what you constructed from the lower bound side. So it must stay within the feasible set. And again, this accelerated dynamics was known from before, but it wasn't really clear where it came from. And now you can see that it actually naturally arises from this conservation law or invariance principle. Also, the technique I'm presenting here, it is generally much easier to generalize. It's not for one method. It is for almost all methods. And you can get more results, especially in non-traditional settings. Yes?
Can you say a sentence about how we are getting a BT? So how are we solving this minimization?
Oh, so this is a standard assumption, is that problems like this are easily solvable. So this is something you will always see in first-order methods. And for simple enough sets, there are choices of phi for which you can get this in closed form. Yeah, good, thank you.
So phi would be like quadratic or something?
It depends on the set. So if it is quadratic, you'll do a Euclidean projection. You can use entropy if your feasible set is probability simplex, etc. Okay. So we've seen continuous time methods. Let's see how to actually get something that's implementable. Because if we want to implement an algorithm, we need a discrete time algorithm. Okay. So let's first do just a quick review of basic discretization methods, known as Euler discretization methods. So if we have ordinary differential equation, this is some vector. This maps Rn to Rn. What forward Euler discretization does, when you discretize, if you move from time t to time t plus h, you get wt plus h times gwt. So you only use what is available up to the previous timestamp. You don't need to look into the future. Backward Euler is more of an implicit method. because instead of having g at time t here, you have it at time t plus h. So you have w at t plus h here and here. And this is not always solvable in a closed form, which is why this is an implicit discretization method. Typically, the way it is implemented in numerical analysis is that you do a few fixed point iterations. And if you have a contraction mapping, then this converges. For what I'll show you next, here is where alpha t becomes important. I want to just take steps of size 1. I can do that because I already told you in continuous time I could choose any increasing alpha of t, so I can just scale it to my step size 1. I will be indexing time by k just to distinguish between discrete time and continuous time. So this is what I get for forward Euler, backward Euler. OK. Here's our continuous time dynamics. In continuous time, v of k is not really what I'm discretizing. I'm discretizing x. Those are my solution points. So effectively, I can just replace the integral by a sum and discretize. That's my vk. Right? One thing to observe here is that this summation goes up to k. So vk, in fact, depends on xk. So if you do forward Euler discretization, your xk will depend on the information you have up to time k minus 1. So you don't need to predict anything. What will happen to the gap, the invariance we're trying to maintain, is that it will incur a positive discretization error. And this is something that harms our convergence. If, however, you were able to use backward Euler discretization, again, an implicit method, then this would give you a negative discretization error in the gap. So this can only help the convergence because you're decreasing your duality gap faster. But yeah, sorry.
Sorry, I'm a little bit lagging behind. Okay. For the very first line, can you tell me again what's the difference between the non-accelerated and accelerated in the first formula in VT?
VT is the same always. XT is different. But in non-accelerated, XT is tracking VT. And then in the end, you just average out overall. Here, you are doing averaging right away, but this XT plays a role in VT.
I guess my question is, how is the invariance principle being changed from non-accelerated to accelerated?
It is not. You just changed the upper bound.
Oh, that's the only thing that changed. Okay.
That's the only thing that changed.
And the upper bound in the accelerated is just the last one?
Yes. Good, thank you.
Okay.
Good. So, you know, the way I've presented this so far, both methods seem to have an issue, right? This one has positive discretization error, so it slows down stuff. This one has negative discretization error, but we cannot really implement it. So let's see what we can do. For forward Euler, in fact, you can interpret Nesterov's accelerated method as doing the following. Do one forward Euler step, and then do a gradient step. Now, what the gradient step does, so this is if the function is smooth. I'm talking about smooth functions here. What the gradient step does, it is guaranteed to reduce the function value. If it reduces the function value, it reduces the upper bound. Therefore, it reduces the gap. So effectively, you incur an error, and then you correct it. Now, I have a recent result with Lorenzo Orecchia that actually gives a different algorithm that comes from backward Euler discretization. The main idea is that the fact that you're incurring this negative discretization error gives you enough slack. So you don't really need to solve your step exactly. You can do it only approximately. In fact, what we show is that only 2 fixed point iteration steps suffice. So, and that's it. That's the algorithm. For both of these algorithms, you can get optimal accelerated convergence rate for smooth functions. You can also extend them to other settings, but this is the basic scenario. Now, another thing I want to say is that this algorithm, we'll see very soon why it's useful. But one thing I want to point out is that initially when we did this work, I mean, it was unsurprising that you can get acceleration through a different way. All accelerated algorithms we had before were based on Nesterov's acceleration for, 30 years or so. Right? So that's one part. But what happens with this algorithm is that we have this first fixed point iteration step. We treat it as some sort of extrapolation. We try to make a step, we see what happens, and then we do another one to correct whatever mess we made. A small issue with it is that this gradient that we use in the extrapolation step is never used again. So this will increase our oracle complexity, our number of queried gradients, by a factor 2 compared to Nesterov's method. Fortunately, we have a follow-up work with Michael Cohen and Lorenzo that corrects this issue. And you can, in fact, get still optimal iteration complexity while having the same iteration complexity as Nesterov. The idea is mainly in the analysis. Because in the upper bound and lower bound, what we were doing is we were treating this just an extrapolation step. And then for upper bound and lower bound, we were using the same sequence. If you offset the two, so if you use this sequence of point xk when you're building the upper bound, and yk when you're doing the lower, xk when you're doing the lower bound, yk when you're doing the upper bound, then this will actually still give you an accelerated method. Because upper bound is kind of gets a little bit better. Yes?
So did you try to use, I mean, I'm not sure if it helps, but maybe it helps in practice, who knows? Like if instead of Euler discretization, you use some other discretization based on more than 2 points.
Yes. We looked into these Runge-Kutta methods, but we were thinking about using this midpoint rule. When you try to work out stuff, you just cannot get that. You cannot get rid of the discretization error. So if you think about taking a step over an interval, in fact, to make progress, it seems like you need to be doing at least a full step. You can make a larger step, but not a smaller one. An example where you take a larger step, in practice, sure, you need to, then even just to solve for a midpoint rule, that will take you lots of inner iterations. There are examples of larger steps in the work by Jonas Sherman on multi-commodity flow.
In the more practical communities, there is a paper by Francis Bach on trying to do those multi-point.
Yeah, so from.
But maybe you knows. I don't remember. What,
if I'm thinking about the same paper, they were thinking about discretization methods where you are in fact using just the gradient flow. So you use all the information, but that applies only to the unconstrained regime. You can see why also from these techniques, because you can, from all the gradients, just construct what you need. Yeah. Okay. Now, I've shown you different algorithms. Let's just see one illustration here. So this is the function I've been using all this time. It's just a little bit tilted. If you do continuous time dynamics, it goes down, it goes up, it goes around. So it doesn't kind of convert. It doesn't always reduce the function value. And if you have seen accelerated methods, you have probably seen this before. The reason is when you're increasing your function value, you're improving the lower bound. Now, if you have seen any numerical analysis, what do you expect will happen when we discretize? Do you expect these methods to follow this continuous time dynamics closely? But later?
Depends how well we discretize.
Okay, let's see. So this is Nesterov. I'm not sure how much you see. It goes like here. This is this AXGD, the first algorithm I showed you. This is this improved AGD that reduces oracle complexity. They take very different paths, and they don't necessarily follow the continuous time dynamics. The reason is this is convex optimization. We don't need to follow the continuous time dynamics very closely to converge. There are many, many paths that can reduce the duality gap. If we follow any of those paths, we will get the same convergence. So these different types of discretization, in fact, give different methods that take very different paths. No?
Use those step size, will all the passes converge to the continuous pass?
Possibly, yes, if the step sizes are very small. Yeah. Okay, so let's see now where these different discrete time methods are really, really useful. And where they're really, really useful is once we don't have exact gradients anymore. So these noise-corrupted gradients, you can actually see them in practice for various reasons. One reason is you're not computing your gradient exactly, you're only estimating it, maybe from measurements or from the data. There are other applications where you may be adding noise intentionally in order to preserve the privacy of the data. Now, there has been some work on modeling this in exact oracle and characterizing what happens for accelerated methods. One such model is the model of Despremont. What the model says, you have inexact gradient, the difference compared to the true gradient, in the inner product with the distance of any 2 points is bounded by some delta. Now, this type of model, in fact, only applies to constrained domains with bounded diameter. They are also more applicable in the setting when you're really thinking about bounded adversarial noise. There was a follow-up work by De Volder, Glinier, and Nesterov, where they introduced this model of the noise, and they say it generalizes the first one. The model of the noise, it now applies also to unconstrained regimes. But what it really is doing, it is modeling rather model misspecification. Without this delta, this is just the definition of a smooth function. So really what this model is doing, it applies to the setting where you are trying to use smooth minimization on a function that's not really smooth. Okay. The model we're interested in here is just inexact gradient model, right? I have an inexact gradient. It is equal to the exact gradient plus some noise vector. That's my model. We, in fact, show that through our techniques, you can recover noise accumulation results for accelerated methods from these previous works. So it is a more general model. Also, you don't need to be so pessimistic and only consider adversarial noise. So if you are in a region that has a bounded diameter, the expected error due to noise, the expected error in the function distance is bounded by the diameter times the expected norm of the noise vector. So this can also apply to the cases even with noise is unbounded but has bounded variance. In the unconstrained regime, the error due to noise now involves these AIs and AKs. So these are actually the sequences of points that determine how fast we are converging. In the inner product with the noise norm squared. Here, we do need that the noise is 0, mean, and IID. Now, if you're familiar with the accelerated methods, by looking at this for a little bit, you can see that in this case, noise accumulates. The reason it accumulates is that these little AIs are linear in I. So this you can think of as sum of I squares. So this scales as k cubed. This scales as k squared. K is the iteration count. So your error increases linearly. This should be less than or equal to in both cases. Okay? But the thing is, if we had, even though the noise accumulates here, if we had a slower sequence of points, a slower algorithm, it would not accumulate. Mainly, if this was constant, these would both be k, and it would just average out. So a very simple idea, start with the accelerated method, run it as long as you're making progress. When the noise becomes overwhelming, restart and switch to a slower algorithm. As simple as it gets. Let's see what happens actually in practice. So the numerical experiments I'll show you, one is for a hard instance for smooth minimization. If you don't know what it is, don't worry about it, but this is where smooth minimization algorithms typically exhibit their worst case performance. Another set of experiments is on a real data set. It is epileptic seizure recognition data set. It contains EEG recordings of patients, some of whom were in epileptic seizures, some of whom were not. It has 178 attributes and 11,500 rows. And I'll show examples for logistic regression and for a linear regression with L1 ball constraints, which is also known as LASSO. Okay. And in all the experiments, I will assume that my noise is a Gaussian noise. And then this is typically what we most frequently see in applications. It is 0 mean Gaussian with standard deviation epsilon. Okay.
The first instance, can you make it much harder by just like coming up with much worse condition number? So here it's something like n. Can you make it like exponential and then it will be blown away completely?
So here we're doing only smooth, not smooth and strongly convex. So it does not depend on the condition number. It depends on the smoothness parameter. Good, thanks. The whole point is that when you take a Laplacian of a cycle, this is the same as doing the electrical flow on a cycle. So it takes a long time for all the information to propagate, because things are kind of loosely coupled. Yeah, good, thanks. Okay. On a hard instance, this is no noise at all. I'm also plotting gradient descent, which is a slower algorithm here just for comparison. Nesterov's is a blue one with circles, and the two algorithms I have shown you, the first one is this one, the navy one. The second one is the pink one, the one that has lower iteration complexity, lower oracle complexity. So in the noisy case, all of them are the same, faster than gradient. Noiseless case, same, faster than gradient descent. Noisy case, you see noise starts accumulating for all of them. Gradient descent is kind of stable, but slower. You add more noise, it becomes much worse. Right? So if we do this restart and slow down, sanity check. If there is no noise, we shouldn't be restarting. There is no need to switch to a slower algorithm. So that's fine. With a little bit of noise, they start stabilizing, have low mean and variance. The two algorithms I have shown you, this AXGD and HD plus, have both lower mean and lower variance than Nesterov's. Add more noise, this is even more prominent. Let's see other examples. Logistic regression, same thing. Noiseless case, everything is converging. You add a little bit of noise starts accumulating. You add more, it's even worse. Do restart plus slow down. Noiseless case is the same. Noisy case, it stabilizes. Even more noise, it stabilizes. The two algorithms based on backward Euler discretization have lower mean, lower variance. Now my favorite example is for the constrained regime, where we don't really need to restart. We have bounded mean. You do noiseless case. Nesterov does much better. It is much faster because it performs much better than worst case. The reason is what is happening at an intuitive level is that because of this one gradient step you're taking, you're using more local information, and you can make more progress. Let's see what happens if we add noise. You add a little bit of noise, it already comes very close to the performance of the other ones. You add more noise, it is much worse. The reason is these two algorithms, they always use, for every step, they use complete information about the gradients. So this may make them locally slower, but it makes them more stable to the setting of noise-corrupted gradients. So you can think of Nesterov as being a more greedy algorithm. It can make more progress, but at the expense of being less stable when you don't have exact information. Now, restart plus slowdown is not really supposed to help you here, at least not with respect to the mean. I wasn't talking about the variance, but you can show that if you do it, it can help you reduce the variance, and that's just this last plot. OK. So now in the, yes?
How you detected when to restart and what did you back off to when slowing down?
Yes, yes, good, great question. Great question, you caught me. I'm kidding. For these two algorithms that I talked about, they fully rely on these points that are constructed from the lower bound. Lower bound, when I talked at the beginning, has the interpretation of the dual that is evaluated at this weighted average of the gradients. So you can think of this weighted average of the gradients as being our signal. So when you have a noise-corrupted gradients, your dual will contain both signal and noise. And the way we decide to restart is when the noise is much higher than the signal. Roughly when signal plus noise, if you take the norm, is equal to the expected norm of the noise. Is greater than or equal to, maybe some constant. But yeah. But essentially, it has like this interpretation. If you don't have enough signal, just do something else. Yeah, thanks. How much time do I have left?
7 minutes.
OK. I'll try to make this relatively fast. I'll go over width-independent algorithms a little bit faster because I really want to tell you about the next part. So we talk about width independence typically when we talk about LPs, positive LPs, or known as packing covering LPs. They're some of the most fundamental problems in TCS and OR, especially because they arise as relaxation of many hard combinatorial problems. In their standard form, they can be written like this. A is non-negative, called packing and covering because these are called packing constraints. These are called covering constraints. The width that I'm mentioning is defined as the maximum ratio of the matrix non-zero elements. So it's not something that we can treat as being polynomially large or small. And we say that an algorithm is width independent if its iteration counts case at most polylog with the matrix width. Now, interestingly, in the TCS community, there has been a long line of work on parallel and distributed algorithms that are width independent. It started with the work on Luby and Nissan, who had this polylog epsilon to the -4th. State of the art is Zeyuan's algorithm with Lorenzo that gives epsilon to the -2. We have another interpretation or another proof for these algorithms in a note that's online. What is really interesting is that you need some sort of fine-grained local analysis to get width independence. If you used first-order methods as a black box, you wouldn't get it. Now, do you think that this is intrinsic to the linear programs? Can you get width independence only for LPs? No. I had an earlier work that I did during my PhD. I actually presented it here 3 years ago. That gives an algorithm has this horrible dependence on epsilon, but that's because it works in a very strong computational model. So it's not unusual, but it is width independent. It is for the class of alpha fair packing. So these are some more general convex utilities. These type of utilities, they arise a lot in practice. These type of problems are typically used in congestion control, multi-resource allocation in data centers, originally introduced in economic theory, but really popularized by the networking community, which is why I even started working on them. I have an ongoing work on getting something better in terms of epsilon on a more relaxed model, and also extending this to some covering problems. Now, the last part of the talk is on block coordinate descent. So far we were working with full gradients. We have this oracle, and we feed it a point, we get a full gradient. Now, the next setting is when we partition the vector of variables into some blocks. And then we feed our oracle a point from the feasible set and the index of a block, and we get a gradient only at that block. Some standard assumptions are that the function is globally smooth, that each block is Li smooth. And to tell you about some results, I will be assuming that this is without loss of generality. I can just permute things any way I like, that the last block is the least smooth one. It has the largest smoothness parameter. So standard algorithms, you have probably seen some of them. Cyclic block coordinate descent fixes a random permutation and goes through each block and either does an exact minimization or a gradient step. There's alternating minimization, which is the same thing just when you have two blocks, but with exact minimization. And there is a randomized block coordinate descent. You fix some probability distribution. Each iteration, you sample one block, and you do a step, either a gradient step or exact minimization. Now, what is interesting is that if you look at the convergence of these algorithms, their dependence on smoothness is as follows. For cyclic BCD, there are two types of results. One depends both on the maximum and minimum smoothness over the blocks. One of them only depends on the global parameter, but it has like this factor that scales with the number of blocks. For alternating minimization, you have the minimum of the smoothness parameters. And for this randomized coordinate descent, you depend on all the parameters. Why I'm bringing this up is that this seems like a very curious case. This is because in this case, we can even have a completely non-smooth block and still converge. And why should this be special to two blocks? The answer is it's not. And I have an ongoing work that shows that you don't need to pay for the least smooth block. The algorithm, the basic ones is you fix some probability distribution, but only over the smooth blocks, first n minus 1. You sample one of those blocks with probability pi, do either a gradient step or exact minimization over that block, and then do exact minimization over the non-smooth block. So you're alternating essentially between two steps. One looks more like this randomized coordinate descent method. One is exact minimization. If you have only two blocks, this is exactly alternating minimization. If you didn't have nth block, this is exactly a randomized coordinate descent method. There is no dependence on the non-smooth block in the convergence time. What's even more interesting is that you can accelerate it. For smooth minimization, you would get the same convergence as in Zeyon's paper with other people, this NU-ACDM, except without any dependence on the non-smooth block. In the next minute, I just want to tell you about some other work I've done. As Seb said at the beginning, my PhD was in networking and wireless systems, and I was working there mostly on resource allocation problems. I have done a lot of work on full duplex wireless, on problems of resource allocation and scheduling. It was a very, very cross-disciplinary work with people who do integrated circuits, and we got an award from Qualcomm and invited papers and so on. More recently, I have worked on the design of optical data center architectures, and I also have work on fair rate allocation and routing in energy harvesting networks. So going back to the big picture, what I talked about mainly is this very general technique from which, by enforcing an invariance principle, we get many methods in continuous time. From there, through the discretization, we can both get known methods and new methods, and we can apply it to non-traditional settings. What I'm interested in working on the future is trying to extend some of these techniques to the setting of stochastic methods and seeing what happens there when we have a noisy setting. And I'm also interested in some problems in non-convex optimization. Thank you for your attention. And the talk was based on this series of papers.
Any question? Can you give some comments on your framework in the beginning to the estimate sequence framework?
Yes, so there are some similarities compared to the estimate sequence. In fact, in some cases, this lower bound is essentially almost the same as the estimate sequence. This just gives more explicit construction of what is happening at an intuitive level. Yes? Yeah.
Because I think the discretized version is
yes, the discretized version, it is like, especially for accelerated algorithms and dual averaging, it is essentially the same. Yeah, thank you. Any more questions?
Okay, if there's no more questions, thanks again.
Okay.